So you'll recall that we have an interface, which right now we're treating as being the boundary of a semi-infinite domain. We have a potential at the wall, which we're writing as phi naught. And we've said that the governing equation in this region is given by this expression. And just to be clear, this is a z, and that is a numeral 2. Now, we took this and in the case where our electrolyte was symmetric, we said that this was our governing equation. And in the case where we could linearize this, we said that this was our expression. So this is the non-dimensional nonlinear poisson-boltzmann equation. This is for a symmetric electrolyte. Examples of symmetric electrolytes include magnesium sulfate, sodium chloride, lithium chloride, potassium chloride. And this is linearized. And by linearized, we mean specifically that phi star is much less than 1 everywhere. And for phi star to be much less than 1 everywhere, the simple way for us to make sure that that happens is to say that phi naught star is much less than 1. Because of the nature of the solutions to the equations, because phi naught is always the largest magnitude potential in the system, once we say that this is small compared to 1, then we know that this linearized equation will work. When we solved the linearized equation, our linearized equation gave us some information about the distribution of the potential phi. It gave us information about the concentration of positive species and the concentration of negative species. And it gives us information about u as a function of space. When we look at the distribution of our potential, we got an exponential decay from phi equals phi naught to phi equals 0. When we looked at the distribution of the concentration of these species, we saw that the positive ions, which for a negatively charged wall, as I'm writing here, these are counter ions, meaning they have a size that is opposite that of the wall. This concentration goes from a bulk concentration up to some higher value next to the wall. That is not well drawn at all. So our positive ions are attracted to the wall, and the density of these positive ions is high near the wall. This is consistent with the fluid having a net positive charge density, because for this wall to get negative, it had to lose some positive ions, usually protons. Similarly, the concentration of negative ions is going from some bulk value here to some lower concentration. And in the linearized case, these two curves are symmetric around this C bulk value. The same amount that the counter ions have increased is equal to the amount that the negative ions have decreased. This is true only in the linearized case. In terms of our velocity profile looks exactly like phi does, with the difference simply being that the boundary conditions are here, that the velocity is equal to 0 at the wall. Here the boundary condition at infinity is that phi is equal to 0. Here the boundary condition at infinity is that u is given by minus epsilon phi naught over eta times the extrinsically applied electric field. Now, at the end of the last lecture, I asked the question, what is the difference between the solution we get for the linearized result? This is what I've shown here. An exponential decay with a characteristic distance that's given by lambda d. Characteristic distance over which this velocity changes is also identically given by lambda d. Characteristic difference over which these concentrations start at a perturbed value at the wall and then decay down to the bulk. Lambda d, lambda d, lambda d. If this is the answer for linearized, how do I expect the nonlinear, the real answer to this problem, to be different? We start with the linearized because the math is easy, but the correct answer is the nonlinear form. What do you think will be different? Will the gradients be sharper or less sharp? Will it change from being monotonic to being not monotonic? Will the color change from green to blue? What do you expect? Roll off faster, meaning that if I start at some value at the boundary, you expect this to decay down to the bulk value, and that will happen over a shorter distance. Why do you say that?
Because of the same function, the scaling effects.
That's exactly right. I mean, what this thing says, if we translate this, in a one-dimensional sense, the Laplacian is just the concavity of the distribution. Right? So this says that the concavity of the distribution, if I take the linearized form, the concavity of the distribution is proportional to the potential itself. Right? So for the linearized case, out here, phi is equal to 0. There's no concavity. This is a straight line. As we get closer to the wall, the potential has a large magnitude, and that's consistent with there being a strong second derivative here. Right? So when I fit my two boundary conditions, phi being equal to phi naught here and phi being equal to 0 in the distance, this gives me an exponential distribution. Right? If I say, okay, wait a second, now let's not use the linear solution, let's use the real solution, written here for a symmetric electrolyte. Now I say the concavity is not just phi, it's 1 over z times sinh of z phi. Right? This is something that goes up exponentially. So if, for example, if phi naught is equal to 25 millivolts, then this, rather than being 1, is going to be 3, or E to be precise. Right? And if this is 100 millivolts, rather than 4, it's going to be E to the 4th. It's going to be closer to 100 or 80, something like that. So this basically says that the concavity here is much larger than is predicted by the linearized distribution. Right? Now from Gauss's law, remember Gauss's law said that the concavity of the distribution was related to a physical thing. What's the physical thing that concavity is related to by Gauss's law? It's related to the net charge density. In fact, remember where this equation came from. This is a big, complicated, glorified thing that says that it's just a Poisson equation that says that the concavity of the potential is given by the net charge density. And all we've done on the right-hand side is written the net charge density in terms of the potential. And they made a simpler form of it, and then a simpler form of it. Right? When we look at the real nonlinear term, what it says is this linearized distribution is really underestimating what that net charge density is. That charge density changes exponentially. It's not linear. It's exponential. So the real solution says that this right-hand side is much, much bigger. There's actually way more charge near the wall than the linear solution predicts. So now if I go back to these graphs and I want to predict what is really given by the nonlinear version, right? And I go back and I write this in terms of dotted lines. The nonlinear version says, okay, wait a second, this concentration is going down, but actually it goes down faster and it goes down really strongly at the wall. Right? And the difference between this, just the fact that this difference is small here and this difference gets big here, is consistent with the fact that the potential is getting higher and higher near the wall. Sinh of z star is getting farther and farther away from z star. In fact, because this governing equation is correct when phi is small, this linearized governing equation always becomes correct somewhere in this system. Once I get far enough away from the wall, the linearized version is always right. So the linearized and the nonlinear version always agree way out here. And a lot of times it doesn't have to get very far from the wall for it to agree. And if the wall is not very strongly charged, maybe they agree all the way. But this disagreement that we see is proportional to the magnitude of the potential. If I look at the positively charged ions, right, this is basically an e to the minus something, right? Because we said that the concentration of these species are proportional to e to the minus delta E over RT. This is going down. These negatively charged ions near the wall are going down in concentration because the electrostatic potential energy is high for them to be near the wall. So this is going like an e to the minus something. This is going like e to the plus something. And so this concentration, in fact, is blowing up. How much it blows up depends on what the potential is at the wall. But if I assume, say, that the potential at the wall is 100 millivolts, this concentration is going to go up to e to the fourth times as high as it was in the bulk. Right? So whereas in the linearized version this was symmetric around this bulk concentration, now you see that the e to the minus term is going down, the e to the plus term is going up even faster. And in fact, if you add up the total charge, or the total ion concentration, not the net charge density, but just the total number of ions, the total number of ions here is starting to go up as cosh of phi. And that's something I'll ask you to derive on a homework problem. Okay, so my ions are changing even more strongly when it's nonlinear. The net effect is at the net charge density, right, which is the difference between these two, right? I thought this was going up a little bit. I thought it was going up as an exponential. It's actually going up as the exponential of an exponential. It's actually even going stronger than an exponential of an exponential. It's going up like crazy. With the net effect being that I have tons and tons of charge density, which means I have tons and tons of concavity. For me to fit this boundary condition and this boundary condition to have a concavity that's really, really big near the wall, I get something that looks like that. A much, much, much higher slope near the wall. Because I start at a really, really big slope and a big second derivative that turns that thing around. Yeah?
I was just wondering, like, the point where this concentration behavior starts deviating from like the asymptote, is that at lambda d, or?
So your question is, where does this happen spatially? Okay, so there are two different questions, both of which I think are worth answering. One is, where do they deviate spatially, and where do they deviate in terms of how big does the potential have to be at the wall for them to start deviating? So let me start with how big phi naught has to be, just because I think that's relevant to put it in perspective. So if you take sinh of 0.2, it's pretty close to 0.2. And if you take sinh of 0.4, it's not that far from 0.4. But it's starting to deviate a little bit. So what that means in terms of potential is that if you're at 5 millivolts, it's totally linear. If you're at like 12 millivolts, there's a little bit of a deviation, but it's just not a big deal. When you get to 25 millivolts, now there's definitely a big difference between these distributions. Okay. Now getting to your question, which is actually a little bit harder. You're saying, okay, when will I see these things deviate? And now I'm gonna delay again, and I'm gonna answer a different question, which is, when spatially does this equation stop working? Right? This equation really stops working when your phi becomes like a lot bigger than maybe 12 millivolts or 15 millivolts. So where that stops working is a function of how high the potential was here. So if my potential at the wall is 5 millivolts, it's good everywhere. 12 millivolts, it's good everywhere. If it's 25 millivolts, I have to say, how far away do I need to go for it to decay to about 12 millivolts? Right? Which, based on the linearized solution of the problem, tells me I have to be, you know, whatever, natural log of 2 times lambda d away to get 25 down to 12 and a half. If my wall is 100 millivolts, now I have to be natural log of 8 away to get that. So that position varies a little bit. But I still haven't answered your question. Your question is, where spatially will I see these curves deviating from each other? And in fact, what you find is that when the linearized solution to the problem is no longer correct, what happens is that these curves will have the same shape far away from the wall, but they will not have the same magnitude away from the wall. So rather than having these things don't, it's not like these things are perfectly the same and then deviate. In fact, what happens is these have a totally different shape here, and then they asymptote to a place where they're both decaying exponentially. They're both satisfying this equation, but the exact magnitude of the nonlinear version will actually be smaller, because we correctly accounted for the fact that there was really strong concavity here, which, if we're going to satisfy the boundary conditions, requires a very strong slope at the wall. And then defining an exact point where these things are similar or dissimilar by a specific amount now becomes difficult to simply prescribe it. So, did you see how I did that? Delay, 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 and then don't answer the question.
Question, yeah. So just going back to what you said, so given the fact that you have a different charge density at the interface now, does that mean that the lambda d is actually different? Because lambda d. So let's break it into parts. So the first thing you said is the charge density at the wall is different for the linear and the nonlinear solutions. So that's true, but I also want to be clear about exactly what we mean. The correct answer is the nonlinear solution. The linear solution is just a thought experiment that we use to help think about things. So if I prescribe phi naught at the wall, there is a charge density, there is a distribution, and like that's the end of the story. We find it useful to compare to the linearized version because the math of the linearized version is really easy. I have this picture, it's just an exponential decay. But I don't want to start saying that the charge density at the wall is different because it kind of makes it feel like one of them is physical. One of them is just a thought experiment. Okay, so then the second part, I forget what the second part was. So the second part is if you change phi naught, you will be changing the lambda d.
Okay. So yeah, the question is if you change phi naught, does it change lambda d? So lambda d is not a function of phi naught. Lambda d is a function of concentration. It's not a function of phi. So it's not a function of phi naught because of phi naught. If you say that you have a given charge density and you change the potential at the wall by changing the bulk concentration, you have changed lambda d and you have changed phi naught. But physically, these two things are not related to each other. They're both affected by the bulk concentration. But lambda d is a bulk property, and so lambda d is a function only of bulk properties. Other questions or comments? Okay. So this is changing. The magnitude of the net charge density is bigger. So now I want to make a different graph, and this graph is of the Coulomb force that I expect to see as a function of space. First in the linear case and in the nonlinear case. So I'll argue that this is the magnitude of rho e times e. The way I'm estimating this shape, rho e, the net charge density in the case of a symmetrical electrolyte, is basically the difference between the red curve and the blue curve. So it starts out 0 here, and then it starts to get bigger, 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 bigger. In the linearized case, this increases as an exponential. The nonlinear case, this goes as exponential of an exponential. And so then this curve looks like, and this shoots off to a very large value that I don't quite have room to show. And again, when I'm plotting this, I'm really plotting something that's proportional to the difference between these dotted lines. When I draw the solid curve, I'm drawing something that is proportional to the distance between these two solid lines. If I draw the nonlinear version of this for the velocity, how do I expect the velocity to be different in the nonlinear case? Or will it be different? Yes? Yeah, we've basically said that U is similar to phi in the electrical double layer, and that's not a function of whether it's linear and nonlinear. So this same change that we see here, we see the exact same change there in the velocity. If I look at the magnitude of the viscous stress at the wall, is it higher or lower? Higher in the solid case relative to the dotted line, or is it higher in the dotted line case? Right, it's higher in the dotted line case, right? And in fact, this is an equilibrium flow where I have a balance of forces, and the Coulomb force associated with the nonlinear case, which I've said is going up like crazy here, the same thing is happening to the viscous force. It's all the same because these things are in equilibrium. So the nonlinear form of the equation says that if the potential at the wall is large, my distribution will deviate from exponential. It's going to become more extreme. That is going to be coincident with a Coulomb force that is more extreme. That Coulomb force is going to be coincident with a viscous force that is more extreme, and a velocity distribution that is more extreme. So you can derive an analytical result for the distribution in the nonlinear case in a number of simplified cases. If the electrolytes are symmetric, you can. As long as one of them has a valence of 1, you can do it. So a 1 to Z electrolyte or a Z to 1 electrolyte, you can do it. We'll focus on the symmetric electrolyte. And in that case, we can write a solution for this phi. This, again, will be a homework problem. And in the case of the symmetrical electrolyte, this is the result that you get. Again, these are Z's. These are not numeral 2's. And this should be reminiscent of the linear form. In fact, the linear form, if you just took the tangent hyperbolic out of this, the Z's and the 4's would cancel out, and you'd be left with phi star over phi naught star is given by the exponential of minus y star. That's what our linearized form is. If we solve the full nonlinear form, again for a symmetric electrolyte, we get this. Right? And it basically says that this decay is a function of this hyperbolic tangent expression of phi star rather than phi star itself. That means that when we look at the slope ends up looking like an inverse hyperbolic tangent. And that's consistent with these graphs that we've shown here. This actually also tells you a couple of other details about the distribution. For example, you asked the question about when these two things match each other. In fact, you can show, as an example, that if you take the phi at the wall and you make it go to infinity, the result for the far field distribution will always asymptote to the same answer. And that answer will be the same as what you would get if phi star was 4 at the wall. This is sort of a detail. You don't need to be particularly interested in that. But what it shows is that when you make things go crazy at the wall, this equation says that the ion distribution goes crazy as well. And it forces the system to always come back to a relatively well-behaved solution once you get to a significant distance away from the wall. Now, the mechanism by which a crazy potential at the wall is shielded in a crazy way is that the ion concentrations go to infinity. But the ion concentrations in the real system can't go to infinity. So the nonlinear poisson-boltzmann equation, we can actually mathematically get lots and lots of solutions that have nothing to do with the real world because they require ion densities that become high relative to, or too high for us to use the point charge mean field approximation. And you'll see that in the later parts of chapter 9, where I'll start talking about corrections to the nonlinear poisson-boltzmann equation that come from assuming that there's a steric hindrance associated with ion densities.